Hi, my name is Dr. Matthew Michal. I'm an adjunct professor at New Jersey Institute of Technology, and I'm going to be talking about impulse and delta functions. The impulse functions that we typically use in differential equations refer to delta functions. This is my video review of the same lecture I've already published, which was my in-class, but I've made a couple of corrections, as well as here will just be in this smaller video format rather than the 40-ish minutes. So here is the shortened version. So for differential equations, we've talked about unit step functions. We've talked about the heavy, which is also known as the Heaviside function. We've talked about forcing terms, but a lot of the times we deal with these functions or deal in real-world phenomena where we have an impulse, a short burst of energy that changes the fundamental nature of the problem. And in these cases, we need a new function to deal with this. We need something that has a sudden, short change, like I said, that has a strong impulse, a strong thing. So suppose we have a differential equation, in this case with constant coefficients, because it's easier to solve with our current processes, much better than series, but with the g of t, that's my forcing term. And this g of t, like I said, is in a short period, size of, say, 2 tau, that's that Greek letter down there, centered around some t naught. So t naught is when it's happening, but it's a short, strong impulse, a strong action on a short time period, and then it goes back to 0. Everywhere else it does nothing. So the question is how can we measure this? How will it apply to differential equations? Well, in this case, if we let this arbitrarily have a height, say, c. Now, I don't know how tall it is. In this case, it's 12. But let's say I have some arbitrarily high power. What happens? Well, I can measure it using integrals, because in Laplace transforms, a lot of what we're dealing with are with functions that don't have easy, smooth derivatives. But integrals, because this is clearly integrable, it's just piecewise, it's piecewise continuous, it just has 2 discontinuities, easily integrable. I integrate it, and it's the same thing on the infinite domain as just on that small domain, because everywhere else it's 0. Plug in my c, it's easily integrable, and we get 2 tau c. In fact, if we choose a value of c as 1 over 2 tau, with a really small tau value, that means I'm dividing by a really small number. And say 1 divided by 0.001 becomes 1,000. 1 divided by 0.0001 becomes 10,000. Likewise, the smaller tau we have, the bigger c we have. Which makes sense because we have a smaller time period, smaller gray region, but has a higher height. But if I choose this tau, you choose this value of c, then regardless for tau, my integral, I, will always be 1. And so we define this function, our g, we typically call this the general impulse function. For any general tau, so that's just how wide my base is, my d tau of t is 1 over 2 tau. And 0 elsewhere, just like we defined earlier. Well, then as we've talked about before, this is just the area of a rectangle, so easy peasy, right? That is an area of 1, regardless of what tau is. Well, remember from our beginning of the problem, we were dealing with a short pulse that goes through. Well, so we want to make the pulse shorter in time interval length, but stronger in, or I guess we just are interested in a shorter impulse time. So what happens? Well, we make our impulse time, tau, as we make it smaller and smaller, our height gets bigger and bigger. So This is a bigger tau. I believe I made this. Yeah, so this is, this bottom one is tau is equal to 8, 4, 2, 1, 1/2. So as we make this smaller and smaller, our tau value, then our integral is still 1. But for any particular value of t, as I make my tau smaller and smaller, eventually it won't cover my d tau won't eventually cover this, because notice it's shrinking to the 0. So eventually, if I make a tau small enough, any value of t on this interval will be untouched by d tau. So that's what I mean by d tau goes to 0. So any value of t that I might plug in, it has a value of 0, but the integral is still 1. This interesting process we call the Dirac delta function. And I probably pronounced his name wrong. He's a famous physicist. Does all sorts of interesting stuff. But we also call it the unit impulse function. And so we call it delta t is equal to 0 whenever t is not equal to 0. Because like I said, we're making our range here smaller and smaller, to the point where unless I plug in t is equal to 0, my delta function is equal to 0. But as we mentioned before, all integrals equal to 1. So the integral still has to equal to 1. Oftentimes, we're going to want to be able to move this around, this impulse function, so we'll center it around a point t0. So rather than, say, at 0 here, it might be over here, and so on and so forth. Usually we'll have some positive t0 value, because this impulse will happen at some time after the start of our observation. Otherwise, why not just set it as an initial condition rather than an impulse? So what is the Laplace transform of this? Since this is the Laplace transform chapter, well, plug it in. It's easier to take the Laplace transform of a nice rectangle, the continuous thing as we've done before, rather than some unknown function that I just defined randomly. Well, not randomly, but some new thing that I'm not sure quite about. So I move the limit outside, and it's easy to integrate e to st over my small domain. Plug values in, pull out an e to the negative st0. Some interesting things start to happen. If I move the 2 in and rearrange my the things inside the bracket, this looks remarkably like sinh, the hyperbolic sine function. And my sinh over sinh of s tau over s tau looks remarkably like what I have for sine of x over x as x goes to 0. And in fact, if I use Laplace transforms, I notice that it also ends up equaling to 1. So my whole limit ends up equaling just that exponential that I pulled out earlier, e to the negative st0, which means my Laplace transform is equal to e to the negative st0. And we set t0 greater than 0 because when I was doing my integral earlier, it wouldn't make sense for it to exist outside my domain because 0 was the start of my domain. Remember the definition of Laplace transforms. So we get around this problem with, say, I want to make t0 equal to 0, and so I just take the limit. And this limit, easy to do, ends up making it e to the 0 or 1. Notice t0 cannot be less than 0, but I can get 1 for t0 equaling to 0. So, let's do an example. Well, it's easy to calculate out. I end up getting 2s squared plus big Y plus sy big Y plus 2 big Y is equal to e to the negative 7s, which is what I solved for. I solved for big Y here. And this, when I pull out a 2, complete the square on the bottom, I notice that I'm going to get a 1 over s plus 1/4 squared plus 15 over 16, which means I need a constant up top to match this. So I end up noticing this looks a lot like sine. Notice how quickly you can end up doing this. I just moved my coefficients from here over the Laplace transform of this, and be careful completing the square and multiplication of a constant, I'm already done. This is what it looks like. Note that because I have an initial position and an initial velocity of 0, which cancels out those pesky initial conditions that would normally pop up when doing Laplace transforms, it means it's boring until it turns on at t is equal to 7. So, let's do it again. Y double prime plus y is equal to 4 delta t minus 2 pi. Well, this normally looks like a complementary solution of cosines and sines. So let's take a look. With my initial conditions being an initial position of 1, and that's supposed to be initial velocity. Oh well. So that's supposed to be initial velocity. When I plug that in, I get s squared big Y minus s minus 0 plus big Y is equal to 4e to the negative 2 pi s. Solve for big Y, move the s to the other side, I end up getting this. Notice this right here is just my basic cosine. This right here describes sine, but with a simple sine with a transform in time. So I end up having this basics solved. Notice when I add this back in, I have my cosine with a turn on in sine. I hope this is helpful, and please leave comments, and if you have any questions. Have a nice night.